Hi, this is ET350, Lecture 22. Today we're going to finish up our discussion on synchronous devices. We're going to look at the Lorentz force and the torque develop equation again. We'll look at torque versus speed, power and torque developed, and then we'll explore some phasor diagrams for constant P developed, T developed, and the input voltage. We'll put that all together in what we call these V curves for a synchronous motor. And then we'll generalize what the power factor looks like. And the last thing we'll do is look at an example and then plot how, or not plot, but explore how a synchronous device behaves in the simulation world. Okay, so let's begin. So if you recall from our last lecture, we had this equation, torque developed equals K BT BR sine delta. And let's review what all these terms meant. So you can see here, this is an amplitude, right? Because you have a sine of a delta and amplitude. And we had this picture. You had your stator coils, you had your three-phase coils in here. And when you hit it with three-phase AC, you get the stator magnetic field that spins at the synchronous frequency. You have your rotor, which has the permanent magnet-like field, and that's where you create BR using either the Ampere's law or they're literally permanent magnets on the rotor. You have this resultant total flux density vector, which is the resultant of BR and BS. And you have the torque angle, which is the relative angle between BT and BR. So more torque angle, more torque, right? And if we were to plot this sign, we would see that as we adjust this BR away from BS, plus or minus, you get either a positive torque or a negative torque, which means you're on a motor side or a generator side, okay? And this is the T max here, all right? Now this force, this torque and force is actually the Lorentz force. And so I just wanted to take a minute to explore why is it from the Lorentz force? Well, if we were to now imagine a stator coil, so let's not go into the AC, let's just imagine a static DC stator coil. So you have something, you have, let's say, current going into the board and out of the board. So if I use my Ampere's law, I'm going to see that BS is going up. So, right, Ampere's law. And let's say we had a fixed permanent magnet to the rotor. And, you know, from our childhood, we play with magnets. We can see that the north and the south are attracted, and you're going to create a torque here that wants to line BS and BR, right? That's actually the Lorentz force. So let's attack it from a Lorentz force perspective, right? So we have a coil, and let's just look at this right side coil here. And let's look at this magnetic field here. So we got a BR, we got a current, and we have a force on this wire. We can use our right-hand rule or our cube. Where do we got it? We got our little cube here. And we can see current goes into the board. We have B going up, the external flux density, and the force on the wire is going to the right. Now, Newton's third law kicks into play, and you have equal and opposite reactions. So the force on the magnet is opposite the force on the wire. And what's it doing? It's rotating the magnet towards the left. The same thing that's going on here, right? So you can see this wire is pulling it to the left. It's centering it. Now, let's say we went too far. Let's say this magnet was over here. Okay, well, now we can analyze the other side and we can see, well, now the current's going up and we can do the same game. I goes up, B from the magnet's going up, and now the force on the wire itself is pulling to the left. However, Newton's law comes into play, Newton's third law, and the force of the wire, equal and opposite forces, pushing the magnet into the right now or clockwise. So you can see this coil using the Lorentz force is centering this, wanting to center this magnet. And this, of course, is assuming a DC situation. What's happening is this magnetic field, of course, going up and down, and the combination of all three is creating that spinning magnetic field, the stadium wave. But this kind of, I hope, shows you how all the 7 fundamentals are coming back in over and over and over. So good. Okay, so let's keep going with this lecture. So what does the torque speed curve look like? Well, if you recall from a DC motor, we had torque and speed looking like this. From an induction motor, it looks like this. From a series, what do you call it? A series motor, it looked like this. But for a torque speed for a synchronous motor and generator, it looks like this, just a vertical line, because it behaves under normal operation at the synchronous speed, right? And this point here, this torque max is corresponding to that torque max. And this torque max over here, this negative torque max is corresponding to over there. And you can see this is where your torque angle is between 0 and 90 degrees. And this is where it's between negative 90 and 0 degrees. Okay, and so we have a generator situation over here, negative torque for positive speed and positive torque for positive speed in a motor situation, right? And so if your angle gets greater than 90 or less than negative 90, breakaway occurs and you lose that synchronous speed behavior, right? And just to restate, the motor operates at synchronous speed under normal operation. Cool, so this is a very simple torque speed curve. All right, so now let's look at power developed. So power developed is torque times speed, right? That's our mechanical power equation. And if we're operating at constant speed, if this is a constant, you can see that power developed is directly proportional to the torque developed, right? They're not one and the same, but if one goes up, the other goes up, right? Assuming that this omega m is constant, right? Now, again, we can bring in our Lorentz force, since we should put Lorentz force, right? Okay, we have our Bill's law is saying this, right? BT, BR sine delta. And we know from our relationships between BR and ER and BT and BA that the torque developed is proportional to the voltage and the rotor voltage and the sign of the electrical phase difference between VA and ER. So this is a mechanical delta torque angle, this is electrical one. And because power developed and torque developed proportional, power developed is also proportional to these quantities, right? And so we'll explore what are the consequences of this. So remember VA, well, let's just bring it over. What are these VA, ER, and sine delta again? Well, let's bring the circuit diagram for a single phase synchronous device circuit again. So, and we want to look at, well, what happens if we constant A and constant power develop and torque develop? But let's recall this. So if we had a single phase, we have like our input voltage from the grid, that's this VA. We have ER, which is our back EMF voltage, and that's coming from the field coils here. Remember, you have your field coils in the middle, and you're exciting it with DC current, IF, and you're using your Ampere's law to get BR, which is the rotor flux, and that ER is proportional to BR. Okay, that's their back EMF, right? So the back EMF voltage times the input voltage times the sine of the electrical angle between these two, right? ER and BA, sorry, not ES and BA, ER and BA, gives you essentially a relationship to power, right? Okay. So if we looked at a kind of a typical phasor plot, what would we have? Let's say VA is just pointing at 0 degrees, sure. And we know by KVL, this KVL vector loop, ER plus ES is VA. So we did this last lecture. And the delta, which is this delta here, is the angle between ER and VA. And remember from our complex Ohm's law of this guy that IA and ES have to have a 90 degrees phase difference where ES leads IA. Now, let's say VA was constant. So let's say that's a constant number there. What's going to happen? Well, what would constant power develop and torque develop look like? Well, we see that means ER and sine delta. If we want this whole thing to be constant, this would also have to be constant. And look at this trigonometry going on. We got delta here and ER. This length is actually the magnitude of ER sine delta, opposite over hypotenuse, right? ER sine delta. So this here, this line is a line of constant power developed and torque developed, assuming VA is constant. So I want you to keep that in your mind. So lines of this point, if this line, this ER hits this point, if I could extend it, but all this would all consume the same amount of power. Interesting. Okay, so we'll remember that. So if we have constant VA and constant power develop and torque develop, let's see what happens as I vary the field current. Remember, varying the field current varies BR, varying BR varies the length of ER. Okay, so let's see what happens. So let's say we had a large power develop and torque develop. Well, we might see something like this, where this line is farther away, right? And so this point 1 has a low field current here. And as I increase the field current, notice what happens to my triangle. It starts shifting to the right as long as I stay on this constant power developed curve, right? Okay, notice the current. IA here is lagging VA, but here look at IA. IA is in line with VA. We have unity power factor. And look at this 0.3 here, where we have IA actually leading VA as I'm increasing IF, right? And this is a result that we saw in the last lecture, okay? What about if I wanted to decrease the power developed? So here I have a large power developed. Well, I'd be on a line that's a little bit higher, right? Closer to the x-axis. And so it's the same idea, right? You have low IF, which means you have a lagging situation. You could tune it perfectly to get unity, but then if you increase it again, notice you get a leading. And also notice the length of IA. Here, IA is big because this is bigger, but here by complex Ohm's law, since ES is a little smaller, IA actually gets a little smaller. And then here, as you get to leading, IA gets bigger again. So that's also another benefit of reducing your, or not reducing, but getting your power factor to unity, is that your current goes down if you have the same voltage. If your current goes down, that's nice because now you're paying less PG&E bills, right? So good reasons to get your power factor in unity. Now let's go to an extreme situation, which is, I mean, not plausible in real life, but let's say we have perfectly no power developed and torque developed, right? Well, what happens there? Well, we don't have any torque angle, right? That torque angle goes to 0. And so now ER and VA are aligned. And if we're in a situation where ER is actually, we have a small IF, ER is actually going to be a smaller magnitude than VA. And by KVL, we have ER, ES, VA, but notice IA is actually pointing down. We have a lagging situation. Now we could turn up IF, which turns up BR, which turns up ER, and make them perfectly the same length. But notice the ES is technically, I don't know, it's everything. ES and IA are essentially 0 in this case. And yeah, I put quote unquote unity because technically if there was any value of IA, it would be pointing to the right, but IA is 0. Okay, if I kept increasing IF, which means I increase ER, which means I get to this situation, now by KVL, ES has to point backwards to connect to VA and IA points up. So we're back to leading again, right? So let's take these 3 plots and put them on what we call a V curve for a synchronous motor, all right? So we're going to plot IA versus VA. And this is, like I said, for a motor situation, all right? And why is it motor? Because in all these cases, the delta here is in a way such that ER is lagging VA, which means BR lags BT, right? So each line is a constant torque developed and power developed line. Look at these. These are all, this is my V curve. So what I'm going to do is I'm plotting IF versus IA, so that field current. And let's look at this first point here, low IF, right? Low IF, and I have a I'm here with a larger amplitude of IA, but as I increase IF, look what happens. I get a smaller length of IA, and then I increase again, okay? So technically, this should actually be a little bit higher. Sorry, I should have drawn that a little bit better. Okay, what about over here? B1, B2, B3, okay, good. So we have the same thing going, but we're going down in torque and power, good. Okay, and then finally we're here, we're having what? Current, no current, and more current, right? And you can see to the left of this dashed line is a lagging power factor, and to the right of this dashed line is a leading power factor, and you can see that from here. So this is what we call a V curve. When we do the lab, we'll actually see this in lab, okay? And these lines are constant power developed and torque developed, and assuming constant VA, okay? So this is what we call a V curve for a synchronous motor. Just as a nice little review of power and power factor, right? Let's look at this. This is a little bit complicated, but I'm going to slowly go through it. So remember, we are looking at a single phase of a synchronous device, right? So we have IA and VA. By KVL, you have the same VA. So these are representing the coils of one phase. And so the power of one phase is just IA VA times the power factor, IA VA times the power factor. Remember, power factor is either the apparent of the real or the cosine of theta V minus theta I, right? And we have a 3 because we're typically dealing with 3-phase systems, right? So what does this cosine of theta V minus theta I look like? We know what that looks like. It looks like this, right? A cosine, right? And I'm plotting theta V minus theta I on the x-axis, and I'm plotting the power factor or cosine of theta V minus theta I on the right, on the y-axis. Now, in the middle, we have a motor situation. On this side, we have lagging. Notice IA lags VA. Here we have leading, IA leads VA, and we're in the kind of quadrant 1 and 4, right? Here we're in quadrant 4, here we're in quadrant 1 for the current. That makes sense, right? And why is IA lagging in this case? Well, theta V minus theta I is positive. So here we have a positive number, which means theta V has to be bigger than theta I. That's why we're here, and vice versa here. Now notice cosine dips into the negative, right? And so here, let's kind of keep marching in our lagging case. Look at this, IA is now lagging VA still, but the current is pointed in the opposite direction of VA, and our cosine would become negative. This would be a generating case where the power factor is negative in delivering power. Same with over on this side now. We have a generator case where the synchronous device is delivering power. And look, IA is now leading VA, okay? So hopefully this is a good summary, a generalizable view of how the power factor and a synchronous device all relate to each other, right? And it's hopefully mathematically consistent, right? And this right here just says, over here, you're having lagging, over here, you're having leading, okay? Not too bad. Let's do an example now. And the example is slightly complicated, but that's good. We want our examples to be complicated. And I hope it starts pulling together all these different facets of what we just covered. All right. So what do we have? The problem says, assume we have a synchronous motor and VA and IF are constant. And there's no stator resistive losses. We have 6 poles. The VA is 240 volts pointing to the right at 0 degrees, 60 hertz. Okay, no problem. And let's say in the first case, you're operating at 50 horsepower, you have a unity power factor, and you have a torque angle of 15 degrees. And they want you to find the armature current, the impedance of the what do you call it, the stator coils, and the magnitude of these two voltages, ER and ES. Okay. Now they have another case where they essentially remove the power, right? I mean, can we do this in real life? Yeah, it's going to be a little difficult, but let's just, this is a toy problem, right? So they say, well, what's the current going to be when you have P developed equals 0 and power factor 2 and delta 2? What are these things, right? Okay. And then plot these on the V curve for case 1 and 2. So let's look at what we got here. So before we dive in, let's just review what all our tools that we have. So I redrew our circuit. So we have VA, IA, ES, ER. Okay, this is the AC. This is our DC circuit. This is only one phase. What do we have? KVL, VA equals ES plus ER. Good. Complex Ohm's law, ES equals IA times JXS, which we're going to need here. And remember, XS is the impedance here, which is constant for both, right? Okay, good. And recall that it's equal to omega LS, but I think in this problem, we're not going to have to worry about this because they didn't give us the inductance, right? Yeah, we're operating at, I guess that would be 377 radians per second. But we are probably not going to be able to find this from the inductance because that wasn't given. Okay. Now we could solve for it later, but we're not asked to solve for this. Okay. We have two relationships. Remember, phasors are just vectors. And if you have a phasor equation, you have two equations, the magnitude and the direction. Here it just says that the angle of this equals the angle of that plus 90. Here it just says the magnitude straight up multiply. And because we're in a motor situation, BS leads BR, which means BT leads BR, which means VA leads ER. Good. And then the last thing is the power. The total power equals 3 times the single phase power, right? Which we have here, single phase power. This is total power, I apologize. Equals 3 times IRMS, VARMS power factor. Okay, so these are going to be our tools in our tool belt that will help us solve for these 3 things, or 4 things and 3 things here. Okay. So let's look at case 1. In case 1, what do they tell us? They tell us that the power factor is 1. So that means that the IA and the VA are aligned. IA and VA are aligned in case 1. That means on a plot, we would see something like this. IA and VA are in the same direction. We also know it's a motor. So that means that a motor that VA leads ER, good. VA leads ER by the torque angle given of 15 degrees, all right. And what else do we know? We know ES by the complex Ohm's law has to be 90 degrees greater than IA, so ES must be pointing straight up. So these are all the clues kind of drawn out, right? So then how could we put it all together? Well, we know by KVL, we can combine the voltages. So we can put these three voltages together in a KVL loop, okay? So ER plus ES has to equal this VA, right? This VA of 240 angle 0. So we can draw something like this. ER plus ES equals VA, good. And we know that IA is pointing to the right, good. And then this is 90 degrees off, and then we have the 15 degrees. Okay, that's not too bad. So now it's, what do we note here? We can see that ER1 is actually bigger than the 240. So we better get a number for this ER1 that's bigger than 240, good. And we can see, of course, IA1, we don't know the magnitude, but we know that the phase is 0 degrees. So we're halfway there to getting that one. And maybe we can play some games with this triangle to find some of these lengths. And I think it's not too bad. Look, we got a length here, an angle. That should be pretty easy to solve for these, right? What do we need? Let's see, we can use a tangent to get this and maybe a cosine to get that. All right, that's not too bad. And then let's say we had this value. If I know this value, and I can maybe use my complex Ohm's law to get the magnitude. So all these tools here are allowing us to take these clues and find out all the unknowns. All right, let's attack it. So the first one is the tangent. Yep, tangent of 15, or that delta is this ES over VA1, good. Which means I get 64 volts. Yeah, that seems reasonable, 64 volts here. Cosine is equal to this over this, adjacent over hypotenuse, good. And we get 248. Yep, 248 is 8 volts bigger than 240. Yeah, I buy that, right? And that's greater than VA1, fantastic. And then what? We have our power developed equals 3 times this, okay? So that was maybe a different way to get the current than I thought. Is that right? Yeah, that would work, because if I know VA is 240, yeah, that works. And then what's the power factor? Oh, it was 1 in this case. That's nice. So this equation turns into one equation, one unknown, because we know this is 50 horsepower. So then we just solve for it. We got to convert it, of course, into watts with our nice 745.6 factor, unity power factor, and it's just straightforward. So we get 51.78 amps, okay? So that's solved for the current. Now, the last thing we were asked to solve for was the impedance here, right? And so this is equal to, from the complex Ohm's law, 64 divided by 51, or 1.24 ohms. Okay, not too bad. So we did have to apply the complex Ohm's law, but this actually helped us find the impedance as opposed to the other way around. Okay, good. And remember, this XS is going to be valid for both cases. So we have all the values here for case 1. So let's go to case 2. So case 2, what do we have? Case 2, we have no load now. Now we got to find the current again, the new torque angle, and the new power factor. All right. So if we have no load, we have to remember what's constant though. Well, it was given to us that the voltage and the field current is constant, right? Assume VA and IF are constant. All right, well, if IAF is constant, BR2 and BR1 are the same because they're dependent by Ampere's law on IF, which means ER2 and ER1 are the same. So that means this was what, 248? So ER2 is still 248 and it's still bigger than VA. That's good. If there's no load and power developed, well, there's going to be no torque angle. So that's easy. So this one was trivial. That's just 0. No load. Boom. Which means if we draw the phasor plot, instead of having a delta of 15, we're actually going to have everything aligned. Okay. And this ER2 is going to be bigger, which means the ES is going to be pointed backwards, which means the IA is pointed up. Okay. And so we get that ER2 is going to be bigger. So this was 248 from the previous problem. This is still 240. ES2 is pointed backwards by KVL, and IA2 is pointed up because of the complex Ohm's law. Okay, and the delta is 0. Well, what do we notice about this IA2? Notice it has an angle of 90 where VA has an angle of 0. And if we go to our power factor equation, cosine of VA minus theta IA is going to give us our power factor, and 0 minus 90. Well, cosine of plus or minus 90 is still 0. So we have 0 for the power factor. Easy. Okay. All right. What else do we have? Well, We have the fact that the angle is 90, but we still need to find this one. So we have these two, we got to find this one. And I think this is actually not going to be too bad because what do we have? We know this one and we know this one. It seems by KVL, we can easily get this one. We know the impedance XS, so we can get by complex Ohm's law this one. And I think that's pretty solved at this point. So let's just crunch it through. And so complex Ohm's law for sure, we're going to get this one. We already know this one from case one, it's unchanged. And this is from KVL, good. And because all these are aligned, they're all in the same phase, you can just straight up subtract them. You can't do that in general if they're all at different angles, but this is all on the x-axis. So you can just take 248 minus 240. So you get approximately 8 volts for this guy. And then 8 divided by 1.24 is going to give you 6.8 amps. And that's this guy here. So the current is 6.8 amps pointed up. Now let's plot all this stuff on the V curve. That was the last thing that was being asked. So here's our V curve, right? Boom, 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 right? And remember, this is a dashed line of unity power factor. Now in case one, because we have unity power factor, right? Case one power factor is 1 for case one, right? We're going to be plotting here, and because we're at a non-zero torque and power, we're kind of up away from this bottom curve, right? And we're going to plot right on that dashed line. Now, remember, we had constant field current, so we're going to just drop down all the way to this no load situation for case two, and this is where we're going to plot it. And we can even like check if it's consistent with our understanding of a V curve, where to the right is leading and to the left is lagging. And we see that we got 90 degrees. Yeah, that was corresponding to a leading situation. So yes, we are consistent with our plot. So this is a nice, tidy little problem. It has some complexity, but it's nice because it kind of combines all the different little concepts into one problem. Okay, so the last thing I wanted to do is actually go into a simulation. This is a Festo online LV simulation to just see this behavior of the current and voltage leading and lagging with more or less field current. So let's jump over here. Okay, so I'm going to show you what I got going on, and I have a power supply here, and this has a fixed 3-phase current going to a synchronous device. Okay, now this synchronous device has a hybrid rotor, which means it is self-starting because it has an induction rotor in the middle of it, right? Remember, if it has just a permanent magnet, it's not self-starting. If you hit it with that synchronous speed that's going ripping at 377 radians per second, or even half of that, it's still too fast to catch that rotor. But if you have an induction rotor, it'll still start up, even though it's not, what do you call it? Typically okay. We have it connected to a dynamometer here. And so here we can measure the torque and speed. And so let's just start this guy up and see what we get. So I'm going to power this up, and I'm going to power this up. And when I hit it with that 3-phase voltage, the field current is actually off. Notice I have this off switch. And notice I'm spinning up, and it spins up at 1680. So this is a 4-pole motor, so it should spin up at 1800 for the synchronous speed. But because it's operating as an induction device, there is some slip, okay? So let's turn this torque down, and notice as I turn the torque down, the load down, it spins up, but it's not quite 1800. Now I can come over here, and let's turn this field current down, or I'm turning this rheostat such that the field current will be low. And I can go click, and notice the RPMs jumps up to 1800. Now what you're seeing on the left here is a plot of the voltage in yellow and the current in blue. All right, so now we're operating at synchronous speed. Yay, everything's happy. I have the voltage and current plotted here on the left. And let's see what happens as I adjust the field current. So right now I have low field current, and let's look, and I have low torque, right? So let's say we have low torque, okay? And torque is 0, or not 0, it's close to 0. I could make it as close to 0 as possible. Now there is still friction in here, and so you technically don't have 0 torque developed, but let's see what happens. So if I am at here, the lowest field current, notice my current is lagging the voltage. And as I adjust the field current up and up and up, look at the current. The amplitude is decreasing, and what do we notice about the phase? The phase is shifting to the left earlier in time. Right here, we have unity power factor at nearly no load. Now, if we could get perfectly no load at the, then this amplitude would actually squash out to 0, right? And then look what happens as I increase the field current, right? We get a leading situation, but the amplitude of the current goes up, okay? Now let's look at what happens as I increase load. If I increase load, the amplitude of the current is going to go up due to Bill's law, right? Let's look at this. Boom. And sure enough, I increase the load here. And are we still at synchronous speed? We are, 1800. So like I said, the torque speed is very simple. It's just a vertical line. And look at this, I'm still leading because I have a high field current. But as I reduce the field current, look, I'm actually becoming more in phase. And look at the current amplitude. The current amplitude is decreasing. Good, so we're now here at unity power factor. We're on that belly, the trough of the V curve. And then if I keep going down even more, look what I get. I get an increasing amplitude of the current, and I get a lagging current, right? So I hope this supports the whole idea of those V curves and the kind of the variable capacitive nature of this. Well, you could even say variable inductive too, right? Because you can make it lag differently as well, all with just the simple turn of this rheostat that controls the field current. Okay, so I hope all these, the theoretical and the practical concepts all came through in this lecture, and you learned something. Okay, well, that's the end of the lecture, and I'll see you in class.